All right, good morning, everyone. Welcome to another edition of the Finite Element Seminar at LLNL. Today it's our pleasure to have Professor Daniele Panozzo from New York University, the Courant Institute. He has his geometric computing lab. Daniele he started his academic career in the University of Genoa. He did his bachelor and PhD there. Then he worked as a senior researcher in ETH, and since then he's been at NYU, Courant. You're doing a lot of interesting work in areas that are very close to what we're interested in the FEM team, power the meshes, robustness in terms of ensuring validity of power the meshes, moving mesh simulations, like the one that we have in our L codes. And today he's going to tell us about some of that, in particular with applications to contact and ensuring robustness when you have a time-dependent simulation. So that's super cool. I'm looking forward to it, Daniele. Thank you so much for agreeing to come and present here. The floor is yours.
Yeah, thank you, Tanio, for inviting me here. I'm really happy to have this opportunity to share some of the work that we did, and it's great to hear that some of these problems are also of high interest to you, and I hope that this might lead to some potential collaboration between my team and FEM. So what I'd like to start with is something that really bothers me, and I'll start by talking about what it is. So a catastrophic failure from Wikipedia is a failure of a system from which recovery is impossible, usually meaning that you need to have a human intervening in some way to fix it. And if you think about it, like most of engineering is about designing systems that do not fail or fail as little as possible. Like if you design a tire of a car, you really want it to be resilient, to not break, to not have a flat. But somehow, one thing that really bugs me is that as soon as we move to meshing or simulation software, catastrophic failure tend to be common and something that people deal with and have to sort of like learn how to deal with. And the sort of like theme of this talk is going to be my attempt at getting rid of that as much as possible. I'm super happy to be interactive at any time. So like in case you want to ask questions, I'm happy to also take them during the talk. And so there are many reasons why this is a very hard problem, like both meshing and simulation are very difficult problems. They involve geometry, numerical methods, physics, modeling. But there is one reason which I think it's really difficult to deal with, and it's so difficult to deal with, which is usually fully ignored. And this is this big assumption that we usually do, that floating point numbers are equivalent to real. Or, I mean, we know that they're not equivalent to real, but we use them, assuming that they have similar rules as real numbers. Unfortunately, this is really not true. And in particular, obvious thing like multiplication distributes over addition is really not true if you're using floating point. Or the gradient of a function is in a ascent direction. This is also not always true, and so on. And so the issue with all of these is that if you ignore them, things mostly work, and this mostly can be a very high number, right? 99.99%, but not all the time. And so if you have cases where you really care about robustness, unfortunately, you should not rely on these rules. And what I'm going to tell you today is a few attempts, especially for contact and for inversion check, where it's actually possible to do it. So you can have checks that do not rely on properties of real and still keep like performances that are reasonable, like comparable to existing methods of use floating point. So this kind of problem is what my lab is working on. I'm co-leading the geometric computing lab with Dennis Zorin, and very lucky to have this group of postdocs and students that are interested in working in this. And I also want to mention Teseo, which was a postdoc in the lab, now is a faculty in Victoria, which is also a collaborator in many of these projects, as he was the one that started the FEM software, which is our finite element simulator, which has been designed to be easy to play with, and is what we use for exploring these topics. And so today I would like to focus on elastodynamic with contact, because it's one type of physical simulation where a lot of this geometric problem shows up. But many of the things that I'm going to discuss are not really tailored only for elastodynamic. They can be used also for other PDEs. But so the sort of problems that I would like to be able to solve is forward simulation, for example, of this complex assembly. This is a lock that at some point opens up. And you see here, you have like a lot of interaction, you have lots of contacts, you have dynamics. And here in this simulation, there are many things that could go wrong. And if any element invert or any pair of triangle intersect, things could go wrong. So the thing that we can do, and I'm going to tell you today, is that we can actually solve simulation of this kind, ensuring that there are no intersection between elements at all, like even accounting for floating point rounding. And the second thing is, for example, in this case, where you have this ball that hits the wall at high speed, there are very large deformations. Another thing that you really want to make sure is that the geometric map of every element stays injective, or elements do not flip. So this is the second invariant. And also in these simulations, what you're seeing here, and every simulation that you see in this talk, we actually have a formal guarantee that elements cannot invert, even accounting for floating point rounding, and even if they are higher order elements. So the reason why I want to push this is because there are many applications where this would be useful. This is something coming from the medical school at the University of Pittsburgh. This is an implant used to support human tissue. And here it's a simulation of this implant, which is sort of like this interwoven collection of fibers. And this is a simulation. But what's happening here is that we're not using reduced models. So this is a fully volumetric simulation where every individual rod is tetrahedralized, and the interaction between the fibers is figured out at runtime by our contact model. The reason why I care about this is because now, if we want to simulate, for example, how this implant interacts with soft tissue, we can actually have a solid tissue, and now suddenly we can simulate the interaction between the two. No shortcut taken here. Accuracy is pretty high. I'm going to describe this in a second. The curious thing here is that, of course, it takes a long time. This simulation runs for days to simulate this expansion here. One very interesting thing is that it turns out that in this specific simulation, the actual material property of the fibers are not so important. Most of the interesting behavior here really appears from contact. So it's a purely geometrical characterization of the material. Here is another one. You see that we're going higher and higher in the craziness of scales. So this is a simulation of the optical nerve of a pig under expansion, like it's being slightly expanded. So the way this was reconstructed was by taking a CT scan of an actual biological sample, identifying fibers, meshing every fiber as a tetrahedral mesh, and then simulating the interaction between all of these. Surprisingly, the simulation here matches the displacement curve measured from the Instron machine by less than 20% error, which is kind of remarkable given the complexity of the scene. And this is an example of a material that is very, very hard to model with a continuum model, while it's surprisingly easy to model with such a system. If you had a way, of course, to model all the interactions that are happening here and dealing very reliably with all the possible inverted elements or contacts that are appearing in here. This is a simulation done with nonlinear elasticity. This is Mooney-Rivlin, and it takes, I think it's like a couple of weeks on a single workstation to run, just to give you an idea of the time scale. And this includes everything, includes like mesh generation and simulation. So not only this is interesting, robustness is interesting for direct simulation, but it's also very interesting if you want to solve inverse problems. So here we have these 4 pieces. The one in the bottom is attached to the floor. We have a load on the right. And what I would like to do is to make it more stronger, meaning that in a forward simulation, we just compute stress. But what I want to do now is to figure out the different shapes so that stress is minimized. And to formalize this a little bit more, I would like to minimize max stress, which can be relaxed in some way, for example, using some pinot as a replacement to make it smooth. And So everything that I showed up to now, handling of contact, handling on inversion, or linear elasticity, needs to be differentiable for this sort of applications to be possible, so that we can have optimization, for example, of max stress, and max stress depends on the result of a physical simulation. So this is a PDE constrained optimization or an inverse problem. And so everything I discussed today is going to be differentiable. What you can do with it, a lot of interesting things. For example, here you see that the interlocking between these pieces gets automatically optimized to become more organic. They start to look a little bit more like bones, which is not a surprise, like, because corners tends to attract stress. This can lead to like measurable improvement in pieces, and so this is really in components. So this is really, if you want, an alternative to doing topology optimization, where you don't need to do thresholding, which introduce unbounded errors, but you can really optimize honestly, solving your full space finite element problem, and then optimizing the shape of your domain. Here are some examples. This is an optimization in 3D, just to give an idea of how the optimizer proceeds. So here it's trying to minimize max stress, while the degrees of freedom are the geometry of this model. This is a full-blown 3D simulation, quadratic elements, nonlinear elasticity. Here is an example of optimizing for a joint between these two pieces under load, and you see that the piece nicely adapts to the other piece, trying to minimize, trying to get rid of corners so that this is reducing stress. If you want to do it at larger scales, you can imagine of using geometry to control mechanical properties. For example, here we are optimizing for geometries of tiles that, when we are used to tessellate the entire space, have a specific material properties. So you have one base material that you use to represent these beams, but then thanks to the geometry, you can actually get different material properties homogenized. If you do this for a sufficiently large space, you can find a collection of tiles that map from material parameters to geometry. And when you have these, you can, for example, optimize object to deforming controlled ways. So here, it's an example where I want to compress it on the left, and what I want to achieve is that it compresses on the right. This is something that material usually do not do. This is possible with our system, which automatically figures out that in the middle, you need to add some elements that have negative Poisson ratios so that it allows this unintuitive behavior. This is one single piece of plastic, but you can see it kind of embeds a mechanism in here. We have possibilities to do this in 3D, so we're interested in solving this problem in 3D. And we're interested in solving this problem when time is present. So here you see a forward simulation of this block falling down, and the colors are von Mises stresses in the block. And here the goal is to see if we can minimize stress not only in one configuration, but over the entire time rollout of a simulation. And this leads to something interesting. So it optimizes the shape of these pins, and now we get a different kind of foam, which is designed to minimize stress, or if you want, to decelerate this block in a uniform way. So this is kind of a very strange material if you think about it. It has like constant force given as you compress it down. Like, this is a very, very strange material, but it's ideal if your goal is to absorb shock. So if you're curious about these, we have a recent paper that describes the entire formulation for being able to differentiate through these problems, but it's not going to be my focus of today. I would like to focus on more geometric problems. Curious thing that you can do with this, you can, for example, figure out material properties by only looking at how an object deforms. So here we are applying some load to this object, we 3D scan it, and only by looking at the 3D scan, we can actually figure out what are the material properties of this object, which deforms in very, very complex ways, because there are, of course, like intersections and large deformations. So the goal of the lab is really to try to make this process as automatic as possible, the forward simulation, for the purpose of being able to solve inverse problems. So ideally, what I would like to have is something where you give me a geometry, you give me your boundary condition, someone is sitting on this chair, and I want to know what happens. If I'm not happy with it, I can change the geometry and then automatically rerun the whole thing and see what's going on. No parameter tuning involved, ideally. If there is complex geometry, it should just work out of the box. Maybe take longer, but it should still work without requiring extra effort. If there is contact, you should just enable contact, it's a checkbox, and then your simulation should ensure that you get something that has no interpenetration and, of course, no inverted elements, no matter what. Just to give you an idea, this is a simulation with 2.3 million tetrahedra, and there are around 5,000 contacts per time step to solve. So it's really a case where you really want to have some guarantees on correctness, because otherwise the chances that some floating point rounding here and there destroys it, it's too high for this to reach the end. So the goal is to get to this system that allows simulation of some PDEs. So now we can do diffusion, elasticity, very, very simple fluids like only Stokes. But in general, the sort of tools and ideas built here could be extended, and I would love to extend this to more complex PDEs. So ideally, no parameters except the one that are really needed, like material properties. And the overall goal is minimize time given an error bound and not have failures. So an observation is that in general, this is difficult. It's a problem that involves geometry. How do you create meshes? How do you model? How do you detect contact? Which numerical method do you use? And so on. And one of the things that I argue for is that this should really be solved holistically, meaning that you treat all of these as a single challenge. The input is a geometry, this is some boundary geometry. The output is an evaluator for the PDE. Everything that happens in between should be treated as a single problem, because maybe by saving something in one place or another, you can simplify your life. So in the lab, we work on a lot of topics on these that I would like to mention briefly. One is what kind of elements do we use? And after looking a lot, we sort of converge that tetrahedra are the best in terms of efficiency. And if you're curious about these, or if you have examples that this is not true, I would love to discuss it with you later on. How to do time integration. And then, like, how do you create meshes? How do you map boundary condition from the input to the mesh automatically? How do you deal with contact? How do you deal with degenerate elements, which turn out to be not such a big deal if you're okay changing the solver code? And then what can you do with it? How do you accelerate it? For example, use curved meshes to reduce the number of degrees of freedom, and applications. So I cannot talk about all of these. So today I would like to tell you about three things. I would like to introduce this new method, which is called, that it's a new way of simulating time-dependent simulation using a formulation which is called incremental potential, which I believe has huge advantages over the more traditional approaches in terms of robustness, while producing in most of the cases exactly the same result. So I believe this is a small change, but a very powerful one. Then I would like to tell you about collision detection and avoidance, and how we can do this with formal guarantees that account for floating point rounding. And then similarly, I would like to tell you about how we make sure that the every element has does not invert, even when they are higher order. And also this is done with provable guarantees. So let's start from contact. So this has been published in quite a few papers. I'm going to give you like a very short high-level overview, which I believe it's enough for understanding how it works, but I'll be happy to dig into more details later on. And we discover this while looking at how people usually deal with contact. And the more common way, and so I want to briefly tell you about contact, and then I'm going to go back to elastodynamic. So the usual way people deal with contact is by taking time steps, figuring out what's happening, and then trying, after you violated your contact constraints, to reinforce them back. This is by far the most common method because it allows you to use implicit time integrators. The problem with this, well, the advantage is that it's very efficient, The problem is that after you violate your constraint, it's very, very difficult to go back. It might not even be possible. And by the way, exactly the same thing happens for inverted elements. Like whenever you have an element that invert, especially if it's higher order, usually you figure out that invert after it's inverted, and then many methods try to bring it back to a valid state. But bringing it back, it's much harder than not letting it happen in the first place. So the problem with these is that now you are sort of at, depending on which parameters you pick, you might get different results. For example, these are a few cubes stuck together, and depending on the parameters, they might collapse, they might self-intersect, or they might be fine. And we try to do this at scale. Every column here is a family of methods that model these non-penetration constraints. Every row is a different problem, and we re-implemented this. And you see here that it's really luck. Like depending which parameters you pick, sometimes it works, sometimes it doesn't, sometimes it gets stuck, sometimes it's very slow, sometimes it just fails. And so we started in this quest of figuring out, can we have an algorithm where no matter what you do, no matter which parameters you pick, there are never going to be intersections. Like, of course, like if you pick a massive time step, you're going to have huge errors in your physical model. You're going to potentially like remove a lot of energy or add a lot of energy. But it should still not have intersections. And so in addition to this, so we want to have no intersection at all, we want to have positive volume for every element, and we want it to be differential. So with these constraints, we sort of came up with a new formulation, which I think it's very exciting, and I think it could be easily adapted to water physics. So first of all, before I go to the formulation, so for contact specifically, one way to solve the problem would be to solve them one at a time, which is something that is very typically done when explicit time integration is done. The issue with these is that the performances are terrible because like your time step becomes smaller and smaller as you have more and more collisions. So for very complex scene, it's really impossible to do this computation. Well, it will take too long. But on the other hand, you have guarantees. So the question is, can we have something which strikes a balance? It allows us to take large time step, and it also guarantees no intersections. So the idea is the following. So let's start from a simple system, just Newton's equation of motion, and we want to integrate through time. Let's do it with implicit Euler. We get our classical system of equations. So now, usually, the way this problem is solved is by finding a solution to this system of equations using Newton's method or something, some other approach. If you have constraints, like contact constraints, you add constraints to this system. And the problem with this is that whenever you're trying to find a solution of a system, you might not be able to find one. And if there are constraints, you might not be able to find one that satisfy the constraint exactly. It might satisfy the constraints numerically, but that's still not a guarantee. So we found this formulation, which is a great paper that I strongly recommend taking a look at from Kane et al. In 2000, where they make this important observation that you can always take any time integrator and you can rewrite it as the minimization of a potential. So now, equivalently, instead of finding a solution to this system, what you can do, instead of solving this system here, what you can do is minimize an energy. And the global minimum of this energy is going to be a solution to the system above. And the two are completely equivalent. So at a first look, this doesn't sound like it's changing much. But the big advantage here is that now, instead of having to solve a system potentially with constraints, we are down to minimize an energy unconstrained. And this is in the paper, they call this incremental potential. That's why we call our method incremental potential FEM. So computing the next time step boils down to minimizing a potential. And this potential, for the case of elasticity, contains information about the inertia and elasticity. Actually, if you differentiate E, the gradient of E is going to be exactly the inertia and elasticity forces that are acting on the system. Now, if we want to deal with contacts, what we could do is add another potential whose gradient are the contact forces, and we can make this potential smooth. And we can make this potential such that it's activated only when objects are reasonably close. Not exactly touching, but reasonably close. In addition to this, it's possible to do a similar trick for friction, which has a star because, of course, like it's not possible to write friction in a potential formulation, but let's just skim over it. I'm happy to tell you more if you're curious about this. It's just an approximation, but a very tight approximation. So now, if we want to compute the new time step, we need to minimize an unconstrained energy. And to do this, we can do it, for example, using Newton's method. Newton's method for minimizing an energy, not to find a solution of a system of equation. But the powerful thing here is that we can now, in the line search of Newton, ensure that the constraints are not violated. So the algorithm will be, for you're at a certain point in your system, you want to find the next configuration at the next time step. This involves minimizing a nonlinear energy, which can be messy and complicated. And this energy, you want to minimize it, so you're going to take steps. And now the step, of course, might actually point toward a direction where the energy goes up. Like, for example, if you have a barrier for contact, there could be a point where it's infinity. But now the only thing that we need to do is to make sure that if we try to take a step that is not valid, in the line search, we're going to take a shorter step. And this also applies for inverted elements. If an element tries to invert, we are simply going to take a shorter step. So the advantage of this approach is that the computation of the direction where you move can be done in floating point, but the actual check of what is the maximal step that you take can be done with exact computation. And in this way, having only to check for how long is the step, it turns out that this can be done very efficiently. So this is a good time if anybody has questions on this before I move on. And if not, I can continue.
Did I ask something real quick? I'm online.
Yeah, absolutely.
When you evaluate these contact constraints, are these sort of like node on face constraints or edge on edge or volume of intersections? Like what is the actual geometric thing which is determining this B of X?
Yes, I am gonna get to it soon. So this is actually a smooth potential, which is written as a double integral over the two surfaces, every possible pair of surfaces. And then this is discretized to something that becomes a sort of like collection of all the possible distances between all the possible pairs of edges or every possible vertex and triangle, if we stay for piecewise linear. You have all of them in this potential, but then since the potential is localized, most of them contribute nothing because the potential is zero if the distance is too far. And so this is what still makes it reasonable computationally and possible to evaluate.
I have a question.
Mm-hmm.
I know people use these, monolithically, converging methods, but a lot of times they get really small time steps because you have to, satisfy that line search or literally small line steps. So I guess the knock on those is they're sometimes slow to converge. I guess they're robust though.
Right. In this case, so formulating them in this way, and in our case, like I was gonna show a little bit later, we solve this problem globally with a direct solver. This actually leads to very large steps. So even if you have like tens of thousands of tight contacts, this still allows you to take large time steps. Of course, like the more contacts you have, the more iteration of Newton you'll need. This is a given. But it turns out to not be much worse than methods that do not do this, that, for example, use SQP or some of these other approximations. And this method is like orders of magnitude faster than trying to solve it with explicit methods. And I'm going to show you some results and some timings later on. Maybe we can postpone this discussion to the end when there's going to be a bit more information. Okay. So one more curious thing that comes from here is that now we know that computing a new time step involves only minimizing an energy. And this energy, of course, depends on discretization. So different discretization might give you different values of the energy, just because this is like this is just a continuous formulation. When we discretize it, we're going to get different value depending on the discretization. But this is a kind of exciting because now we actually have a very simple criteria to decide when one mesh is better than another. Like one mesh is better than another if after you minimize this energy, you get a smaller value overall. So, and what is cool here is that this directly accounts without heuristics or anything else for both refinement needed for inertial elasticity, for contact, or for friction. And so we use this criteria, so pick the mesh at every time step that minimizes this potential in our adaptive remeshing method. And we show that this is quite remarkable. It creates meshes that have very few degrees of freedom, only selects the one that are really needed, making these something that can be done in a distributed system or that lead to major speed up. It's something that actually Max, one of my students, is interested in, and I think this is something that Max and Sanyo might have discussed at some point. But I think this is kind of interesting because now it's very easy to decide if you want to refine a certain region of a mesh or not, or if it's okay to coarsen, because you only need to check if this energy is smaller or larger. And here is just like a collection of example where this remeshing is happening and showing that this makes a big difference. Like being able to refine correctly actually dramatically changes the rollout of a simulation. Especially for like nonlinear problem. Here is a nonlinear elastic problem. You see that on the left without remeshing, fixed mesh, and on the right with adaptive remeshing, the actual result is completely different after some time. Okay, so what are the difficult things here? The difficult things here are deciding what to do in the line search and deciding how to integrate these potentials. And so that we can then use them in the Newton method. Like you need to be able to do integration of this potential for computing the descent direction, and you need to be able to do exact checks on the line search to make sure that the energy is really decreasing and you're not hitting these points where the energy is infinite. And so the first thing that we're going to look at is how to deal with this for contact. So this is an example of this potential that I was mentioning before. This is an example of a potential from this point to the surface. You see that like it's doing what you kind of expect. Like as the point gets closer to another object, it's adding some force, pushing it. And you can make these barriers as tight as you want. You can make these, you can push these curves more and more to the left. The more you push it to the left, the closer you get to the more classical discontinuous contact formulation. The disadvantage of doing it is that you get problems that are numerically harder to solve, so it needs more iterations. So if you're curious about this, we have this paper on arXiv that explain how this potential is written down. And we have an entire implementation, if you're curious about trying it, that only computes this potential and makes it reasonably easy to integrate into other FEM systems. But the key thing to figure out is how do I detect when there is a collision? And I'm going to study one of the two cases. So here we have a point which is moving through a linear trajectory. We have a triangle, which is also moving. Every vertex is moving through a linear trajectory. And I want to know if at some point in this trajectory they touch or not. So one of the earliest papers that looked at this was from Snyder in 1992, which proposed the more direct formulation of this. We can write this as a system of equations that has three variables: time, which is where a point is on one of these trajectories, and two barycentric coordinates to identify a point on the triangle. And then they ask if there is any point in time for any set of barycentric coordinates such that the point is overlapped with a point on the triangle. This is just barycentric interpolation. This method is very robust. It uses bisection to find if there is a root or not in the system. And this was very, very quickly abandoned because it's expensive, in favor of the more modern formulation, which is actually univariate. So the idea of this formulation is to, instead of adding 3 variables, reducing it only to time, and then you do the following check. So you have a triangle, you compute the normal of this triangle, which is called n, it's this one here. And then you pick a point, you have your point moving somewhere, let's say this guy here. You pick one of the 3 corners, it doesn't matter which one, and you define a vector connecting the two. And now you want to check what is the angle between the red vector and the blue one, and you want to know if this is 90 degrees or not, which you do with a dot product. Right? So you are checking if this point is on the same plane of a triangle. This is what usually leads, at least for linear elements, to solving a polynomial of degree 3 or 6, depending if you have minimal separation or not. And this is more or less the default of how these problems are solved. Unfortunately, this has a major downside, which is that, for example, let's take this simple case where you have a triangle and a point, and they are all moving together, and they are already in the beginning on the same plane. Now you have this very annoying problem that this polynomial in T has infinite roots, while the original polynomial on T, U, and V has actually no roots because they never touch. And so most contact paper actually start to enumerate what are the possible degenerate cases and have special code which is handling all these cases. Unfortunately, these are very difficult to enumerate. And if you do this in floating point, it's even more difficult to make sure that you're not missing something. So unfortunately, as far as I know, this paper from 92, before our paper, is the only one that actually works correctly. Everything else published after this is not anymore. And so what we did was take a bunch of simulations to create data sets of possible collisions with polynomial systems. We use Mathematica on all of them to do algebraic solutions to find what are the real roots so that we have ground truth to actually check how methods perform. And then we tried existing methods. Also here, every column, every element here is a different method. And what we found is pretty disheartening. So many methods, the large majority of the popular one, this is what are used in major packages, they actually have false negative, meaning they miss collisions. And so this is very dangerous, right? Because you could at any point have a completely failure in your simulation just because you completely missed 2 object touching. One way to fix them, which is, I believe, how many of these actually work in practice, is that you can tune parameters for these floating point methods to actually be over-conservative. So you now have methods that very often, even if there is no contact, they tell you that there is contact. But this is because they have massive numerical tolerances in their solver to make sure that they don't miss it. So in our data set, there are no false negative, but this doesn't mean that it's not possible to construct cases where they fail. So in the paper, we actually have counterexamples for all of them, which are synthetic, to show that you can break them. This method, IRF, is actually the original one from 92. This one works well. It has few, this is log scale, right? So this is pretty good. It has very few false positive. It has no false negative, as you would expect. But unfortunately, it takes a very long time. Like the running time is very high. And so what we propose actually is that by being careful on how we design our algorithm, you can take this algorithm to something which is comparable to the best method that does only floating point, but with strong guarantees and with an answer which is always conservative and in a very reasonable time. Okay, so the overall idea is to use bisection root finding using intervals. I'm gonna just briefly give an overview in case someone is not familiar with them. So the idea of this argument is that you have a function, we have this one here, and we now want to build what is called a inclusion function. So an inclusion function is a new function derived from the original one, which takes as input an interval on the domain of a function and gives you as output an interval on the codomain of a function, which is what you see here. And for this to be an inclusion function, the output interval needs to contain all the possible values of a function within the input interval. Okay, so it's sort of like telling you in this region of the domain, what is the maximal range of values that the function can have. So if you have this, then finding roots becomes quite straightforward. So you can take your input interval, the full interval, you evaluate it, you see what you get. If what you get intersects 0, then there might be a root in there. And so what you can do is you can split your interval into 2, and you repeat. And you do this recursively until you either figured out that there is no root, so all the green intervals are either above or below, or you stop refining and you decide that it's very likely that there is a root in there. What you need, the tricky part here is how do you build this inclusion function? And there is an entire literature on how to do this. And one way that you might be aware of is to use the interval type. So if you implement your evaluation of a function with an interval type, then by construction, you get an inclusion function that has these two properties. It's conservative and it converges. Converges just means that as you make the interval on the domain smaller, also the interval on the codomain gets smaller. Our algorithm uses this basic idea. So we just start by evaluating the entire interval. For us, interval is in 3 dimensions, right? So it's using the original multivariate formulation for contact, so that we do not need to deal with any corner case. But the tricky part is how do you define this inclusion function? And unfortunately, I cannot give you the detail here, but in the paper, we show that for a specific polynomial, the system of polynomial that comes out from this contact problem, we can create an inclusion function without using interval. It's just a simple floating point expression, but as long as you evaluate the floating point operation in the correct order, so because this needs to account for floating point rounding, then we can create this inclusion function with only floating point computation. And that's how this is so fast, because at the end of the day, we have no intervals in here. Everything is pure floating point, but we still have these guarantees. In terms of running time, we have down most of the cases to microseconds. There are a few queries that might take longer, especially if you really push it and you get things that are very, very close. But overall, this is in microseconds. This is, however, not the end of the story, because this only allows us to check if there is an intersection or not. So it allows us to decide how to stop before we hit something that we are not supposed to cross. But on the other hand, computing this descent direction is also not straightforward, because the contact potential diverges when there are contacts, and we need to make sure that whenever we integrate the potential, we account for this. Otherwise, you're going to have some condition in the line search that are not taken into account by the numerical solver, and you might get stuck, which is very likely what was brought up before by one of the questions, where like if Newton is taking tiny, tiny steps because he cannot make progress, what is very likely happening there is that the condition that you use in the line search, which is no contact, is actually not properly accounted for in the potential, which is not integrated correctly to diverge when there is a contact in the discrete, after it's discretized. This is very likely the reason why some of this method takes very, very small steps. So this is, again, very tricky to do this quadrature correctly. I refer to the paper for the details of how it's done, but the sort of high-level pitch is that we use the collision detection to find the closest point, and then we change quadrature so that that point is one of the quadrature points. And so that the discrete quadrature also diverges in the same way as the continuous counterpart. And this is absolutely crucial. So without this custom quadrature, the method does not work at all, or it does work, but it's very, very slow at converging. Okay, so I'm running a bit late, but I'll try to wrap up in 15 minutes. So the second topic is how do you check for validity of a geometric map? So here I would like to open a quick parenthesis first to just make sure that we use the same terms. So by geometric map, I denote the map that goes from the canonical element to an element of the original mesh. And then in addition to the geometric map, there could be a FEM basis defined also on the canonical element, which is what we use to represent our physical quantities. Now, if we do elastodynamic simulation, there is an annoying interplay between the two, because our final mesh is going to be the combination of first the geometric map, and then the application of the displacement, which is stored on this basis, to the original element. So both geometric map or FEM basis could be nonlinear, and both, if you're using it to represent displacement, should really be injective, at least. Otherwise, there are going to be non-physical configurations appearing. So the algorithm that I propose works for arbitrary order for both, and it really doesn't care that these two are not the same map. So just for simplicity, I'm going to refer to geometric map as the combination of being a geometric map and eventually having some displacement defined on top of it, because the algorithm does not really care. If you are interested in using this for something that doesn't change the mesh, then it's enough to probably use this to validate that geometric map is locally injective once and for all at the beginning. But for elastodynamics, it's actually more tricky because the solution changes the geometry. So this check needs to happen all the time as we update the solution. So the formulation in general is you have a nonlinear map from the reference domain to your element, and let's call it X for simplicity. And what we want is we want to enforce that the Jacobian of this map, the determinant of the Jacobian of this map, is positive everywhere on this element. Everywhere is a strong word, because if it's linear, it's easy. You pick any point and it's fine. But if it's not linear, this is really something that has to be tested over the entire element. So many finite element code, especially commercial ones, don't do this. And what they do is they only test this condition on the quadrature points, which is because anyhow, the evaluation of whatever function that diverges when the elements invert is only evaluated at the quadrature points. So it's going to lead to something that often doesn't crash. But checking it at quadrature point doesn't make it right, because you're still going to have inversion somewhere else. And actually, this is really a huge problem. So after we noticed this and we started trying to do some statistics, we took all simulations that we had in PolyFEM that use higher order elements for doing elastodynamic, and we noticed that in all the simulation with higher order elements, now that we have a proper check, it actually detects invalid elements in all of them. So we actually were not able to run a single simulation without invalid elements until very recently. And we were not even able to check if these were invalid or not. So this is one thing. So it's absolutely not enough to check on quadrature point. You need to check everywhere. There is this paper that you might be aware of. It's using GMSH from John in 2014. They have a method for doing this check for positivity, but unfortunately that method is not conservative because it doesn't account for floating point grounding. So it's much better than testing at quadrature points, but it's still not giving you a guarantee. In addition to this, even if you had this, even if this method was actually able to give you the correct answer all the time, this is still not enough. And this is because we are completely ignoring time. So here we have a triangle, a higher order triangle, and you see that the nodes are moving around. And here you have like a beginning of time step, which is valid, an end of time step which is valid, and you have an inversion in the middle. So actually, this trajectory is not a valid one. And so it's really not sufficient to check after a time step. It's really something that needs to be done along the entire trajectory if you care about having a fully valid physical trajectory. I was curious if you can make this happen only with higher order or also for linear, and the answer is you can do it for linear too. But it's very, very unintuitive, and I don't think it's worth to spend a few minutes to actually try to understand what this is. I just hope you trust me. It's possible with linear trajectory in a linear triangle to get it to flip twice during the trajectories. So how do we do this? So the idea that we propose, I think in retrospect is a very obvious one, but I couldn't find it anywhere else, is that we can take a triangle and convert it into a prism where the outer dimension is the time. And now if we do this and we ensure positivity of a Jacobian over the entire prism, this is going to give us an answer which is conservative. So this is a generic construction, can be applied to any kind of element, which just adds an extra dimension. And then you can use something similar to bisection as what I showed before. However, this is considerably more difficult to do because now you have this extra time dimension that needs to be handled in a different way if you want to get something that converges in a reasonable time. I'm not going to go over all the details here, but just give you the high-level pitch. So the high-level pitch is that we are using the basis conversion that John and et al. Proposed to do all of this in Bezier form because the inclusion functions are much tighter there. We have a very important step, which is that instead of trying to be accurate at runtime, where it's very expensive, we actually managed to do a large precomputation of the algorithm using SymPy. It's all analytic. And then at runtime, we have a tiny, tiny expression to evaluate that can use interval to account for rounding errors. So we have an algorithm which is a sort of a Frankenstein because it's mostly running before in a precomputation, and then at runtime is just using a table. But it turns out to be fast and provides bounds. And the algorithm is quite tricky. I'm really running out of time. I cannot go over the details, but I can show you some simulations where it does work. And I can show you some timings just to give you an idea of how long it takes. So maybe let's look at tetrahedra. Linear ones are in the order of microseconds. When you go to quadratic ones, it's a bit more expensive. So we are now at, on average, like 200 microseconds. One thing to note here is that this is trivially parallelizable. So if you have a machine with enough cores, this is very unlikely to be the bottleneck in the simulation anyway. So what we found is that these are reasonable numbers. Even up to order 3, this is usually not the bottleneck in the simulation. They get slower and slower with tensor product element, of course, because the order of a tensor product element grows much quicker than for tetrahedra, because you always need to take the product of all the different 1D pixels. It turns out that for this is for quadratic elements, sorry, this is for linear elements, it's actually faster than checking on quadrature points. So depending on what you're trying to do, this might actually be slightly faster than traditional method, at least for the static check. This is static check only. Similarly to before, you need to be careful here because having this exact check tells you how far you are free to go. But now you need to make sure that the direction is also aware of these potential spikes that are happening. So the quadrature also needs to be done carefully. And here, the reason why we cannot do exact quadrature is because in many of these nonlinear energies, there are some logarithms appearing here. So it's impossible to have standard quadrature rule, but do it exactly. So what we found is that one way to do it is to use the hierarchy that is constructed by our algorithm to figure out if the element is positive or not. We can also use this hierarchy to derive automatically a per element quadrature rule. And we use this quadrature rule for integrating the elastic potential. This sounds like a crazy thing to do when it's very, very expensive, but it's actually not, because few elements, like a tiny percentage of element actually require more than one level of subdivision or any level of subdivision at all. So in practice, using these as a negligible effect on running time overall on a large simulation. But this is crucial because not doing this, again, leads to many small Newton steps because your line search is inconsistent with energy, and so it's going to block it and not allow it to proceed. With this, it's much better, and I just refer you to the paper for more details on this. So to conclude, I try to put everything that I work on and my group works on as open source, and hopefully having other people that use this. So I didn't talk about it today, but we have a collection of algorithms for doing tetrahedral and triangle meshing robustly, which are called wide meshing. Everything that I discussed today about collisions and inversion is actually on separate Git repositories. This one, it's actually completely standalone, so it's something that can be taken and integrated into another finite element system. The code for the positivity check is not online yet. And then we have PolyFEM, which is a sort of didactical finite element code, which is designed not to be particularly efficient or distributed, but is designed to be easy to play with. So there are many features in here, like changing element type, changing element order, having mixed element order. They're all very simple because the code was designed to be modular from the beginning, of course, making huge compromises in terms of scalability and efficiency. So the way we develop many of these methods is trying to prototype things inside PolyFEM, but keeping the code cleanly separated from PolyFEM so that it can be used in larger and more serious finite element codes. This PolyFEM contains everything that I showed you today, and all the simulations that I showed today are coming from here. So concluding, I hope I at least pitch your interest on this formulation. And to conclude, I would like to show you some larger simulations. So this is a context simulation of this duck protected by this microstructure. And this microstructure is actually fully volumetrically meshed. So there are tetrahedra all over inside this foamy thing, and the object is falling down. You see that as it falls down, there is a lot of stress on this poor duck. And so we can use our differentiable simulator to change the geometry of this fall, so that we can actually optimize it to better absorb shock. And we are getting this other foam, which is much better at absorbing the shock. You can already see it visually that it deforms much more than the other one. And this actually reduces the stress on the duck by around 72%. And again, what you're seeing in here, everything in here is meshed as a volumetric mesh. So there are millions of tetrahedra in here and inside the duck. And then this is forward simulated using this approach, ensuring that elements do not invert. And they really do try to, especially in these configurations, and there are no set intersections. So this is a more like Christmassy take as we are getting into the season. This is a softer one. And to conclude, I would like to just show you that this is not only in simulation, but also for it actually matching physical experiments very closely. So we did some mechanical testing on these, more details on the paper. We are off by 10-15% on the displacement curves, strain force curves on these very complicated setup with contact and then high displacement. And so I'd like to conclude here and thanks all the sponsors for supporting this, and thank you again for the invitation to speak here.
I have a question on how you perform the positivity check for the Jacobian. So you're doing the Bernstein expansion, correct? And you check to see if you have any negative coefficients.
Yes.
If you have negative coefficients, do you do any further checks to see if it's actually negative, or do you just assume that it is?
So we are going to continue. So we are going to continue to, it's going to continue to refine until we find like an entire interval where all the coefficients are negative. right?
Okay.
So we can be sure that there is an inversion there.
And do you have some maximum level of refinement you go to?
Absolutely. So there is a maximum level of refinement, which is a tolerance that can be configured. And after this, if it's not possible to resolve it, we just decide and give a conservative answer, but it's very likely that there is an inversion there.
Okay, thank you.
Can you prove that you need a fixed number of refinements?
No, so what we can prove here is that our code will always give you a conservative answer. So if there is an inverted elements, we are always going to tell you that it's there. We cannot say anything about if it's not there.
Okay. All right.
So if it's not there, we don't know. We might be able to tell you that it's not there or not, but you can decide how accurate you want to be with this check with one parameter. And these parameters sort of trade-offs how accurate you are with how long you are willing to wait. One of the interesting things of working this Bezier form is that for most elements, one level of refinement is enough, or not even one level of refinement. So it's very, very bimodal. I don't have results here, unfortunately. Well, yeah, we can look at it here. So you can see that like there are elements that take a much longer time than others, than the average. But overall, there are very, very few where it really gives up. Like this is one of the things that we are still trying to figure out exactly how it's playing, how does it work? Because what we found is that in all the cases that we have with tetrahedra, we never managed to create an example from a real simulation where we run out of iterations. So we are always able to figure it out without running out of iterations. For tensor product elements, so cubes or prisms, this is not the case. There are some configurations that look reasonably benign, but where we run out of iterations. And I only have evidence of this. I do not understand it yet. It's possible that like with its tensor product, you tend to have higher order polynomials, so it's just more likely that this happens.
And just to clarify, one major difference here with the GMesh paper is that you're doing this with interval arithmetic, so you take into account the floating point, the potential floating point,
Right.
Around the fissures.
Yeah, so there are three differences. So one is that it's a different problem because we do this time dependent, not static.
Sure.
So that's one. Then in the Jonen paper, they do this change of bases at runtime, which is actually very expensive and totally unnecessary. So we do all of this in a pre-computation once and for all. So this dramatically improves performance over Jonen. It's like another factor of 10, 20, depending on the degree. And then in addition to this, since the new computation that we do thanks to this pre-computation is very simple, we can afford to have intervals in there to also account for floating point rounding. And so, yeah, so these are the differences. And I think the time-dependent one is actually an important one because you might get into the, if you don't do the time-dependent check, you might have things that flip and then get stuck and then you cannot fix it anymore.
Yep.
So I think like I believe much of the robustness here is really coming from the time-dependent formulation and actually preventing them before they appear.
Agreed.
Which I don't know, like I mean I'm hoping we will see what the reviewer says, but I couldn't find it on any other paper, surprisingly, which was kind of a surprise to me because like this like it seems natural to actually check it over the entire time. Like checking it at the end seems to be an over optimization, but somehow it's what everybody has always been doing, as far as I can tell. I'm not aware of a paper proposing this.
I'm not aware either. Yeah, no, and I agree wholeheartedly. Brandon, you have a question?
Yes. Yeah, so that was a very enlightening talk, Daniele. Very, very much appreciated it. So I've been working with Michael Tupek. He asked a question earlier. We've actually there's some overlap. It was interested in this because we've been doing sort of minimization based problem posing, right, for a similar for robustness, right, and came to a lot of the conclusions that you did. Although this stuff here about with what you're doing here for the subdividing to try to check it, not just at discrete points it was enlightening. It was a new thing to me, and I think that's very interesting. I just wanted to ask. There was a clarification. It was a point that I think is important. I want to understand. So, the minimization thing, of course, like it gives you a framework where you can know part of the robustness because you know, right? Like there has to be a minimizer, and if you can, it's a way to search for it to know that you have a valid configuration and it's the best one, right? It's the correct one. But what I didn't understand fully is how. So we've seen these problems of like what Mike Pusso was asking about, like where sometimes your Newton steps can be they're not really Newton, but necessarily. But anyway, your nonlinear solver steps can be very small because you have these barrier functions that grow very fast, right? Or you have like you said with the neo-Hookean, the log terms, like right, like and very small distortions of those elements quickly lead to very big growth in energy. And so it's so I was trying to understand, it seemed like something that you were describing about changing your quadrature in both of those cases, both in, and I want to understand how does that make your nonlinear steps be larger? I mean, how do you get around, what is the key there, the connection there?
Yeah, so let me try to describe this in a different way, because I really think this is a crucial point, and it's something that, at least for us, it took us quite a while to figure this out. So in general, technically, this line search check would not be necessary, right? Because you are minimizing an energy, so if you're taking short steps, technically you don't need it. It should not happen. You should not ever pass through a point where the energy is infinite, right?
Sure, yeah. If you are willing to take, yes, I agree. In principle, that would save you, right?
Right. So now the reason why you are adding this is because you want to use this like quadratic approximation or whatever else you are using there better, and you want to take a longer step.
Yes.
Okay, so, but now let's going back for a second. So why do we have this line search? Well, we have the line search because since we are using this quadratic approximation, the quadratic approximation will not be able to capture point at infinity, right? I mean, it's quadratic, it cannot do it.
Sure, yeah.
So what you're doing is that you're adding the line search to allow to still be able to find these points where the energy goes to infinity so that you don't cross. Now, it's absolutely crucial that as your point moves closer and closer to this point at infinity, right, that your quadratic approximation will be able to capture it better and better as you get closer, right, because it becomes easier. So what is important is that whatever value you are using for computing your quadratic approximation needs to be consistent with the condition that you use for the line search. So to just rephrase, the discrete thing that you are using to compute your gradient needs to integrate and go to infinity if the condition that you use for the line search tell you that there is a point at infinity there. So the two things are really, really related. So you don't need the line search. You are adding it there because you want to allow bigger steps, but you still need to make sure that whatever you're using to compute your step is aware that there is a point at infinity there. And
yeah,
okay.
yeah, I see that. It's just okay. I don't want to take. I'll have to go read your papers. It seems to me that you need to do that so that you don't step through it and get to the other side. But nevertheless, your step is still shortened. You just can't take a step that goes any bigger than climbing that hill to infinity, and so that could be small and can sort of stagnate if you, or at least crawl. You'll get there eventually, but.
I agree. So I agree with this. So what I'm saying that is absolutely lethal, and I saw other codes where this happens, is that you say, well, I don't want it for contact, right? For example, you say, okay, well, I don't want to have contact, so I add something to the line search, but then the way you compute your gradient is actually not aware, is not exactly consistent with a line search. And this is absolutely lethal, because then you're going to get a direction which points you toward this point at infinity, and this is going to be stopped by the line search. And then it's going to continue to try to go there because it doesn't know that there is a point at infinity there.
Okay.
Okay. And this is really, so this is something which is very hard to debug because the inconsistency can be very small, and this really like dramatically slow down whatever algorithm you're using there. The way we do it actually is that we don't do Newton for these, but we use a cascade of robust solvers. So what we do is that we first compute the descent direction with Newton, and we try to go in that direction. If it's too small, we do it again by using a Newton, which is projected to an SPD matrix, because sometimes it helps. If this does not move, we use gradient descent. And if gradient descent does not move, we do stochastic gradient descent. And we do this in this like hierarchical way, and this is what really gives it robustness, because after you sort of shake out of this bad minimum, then it can move away.
Well, thank you. Yeah, thank you. That's very enlightening.
So if you're curious about this, we are using a software package that we developed called Polysolve for this, which has this whole strategy in there, and it has like a gazillion of linear solver wrapped up. So we brought this to benchmark linear solvers. But this robust Newton, we call it robust Newton, but this is another like important ingredient to make all of this work.
Thanks a lot. Yeah, I'll take a look.
I have a question. When you build these models, sometimes they have thousands of parts, and they already have inclusions at the outset, because the model wasn't able to preclude them during the build. The parts, they don't all fit perfectly together. And the barrier function is going to basically choke on that, and yet it's a problem where since it's unbiased, you start trying to move those nodes. Do you have a problem? I don't know if you ran a lot of these problems, because I imagine a lot of them you always start out without any initial conclusions. Did you get any problems with that?
Right. So we cannot handle. So if the original model has self-intersecting elements, we cannot do anything. We cannot even start to simulate.
Yeah.
So the way we deal with this is that we actually have a set of meshing tools that can clean up this for you. So either from a CAD, so you have multiple options, right? The default one, which is what was used for most of these cases, is that we remesh objects, and if two objects are touching already in the beginning, we just treat them as the same object. We just fuse them together. And we have tools that can do this reliably on CAD models. The main one is called Tetwild, but I think some of you might have used at some point. And this one works reliably, but of course, if two things are overlapping, it's going to fuse them together.
Yeah.
We have a new one, which is going to come out soon, hopefully, which is instead working. This is mostly designed for some of the biomedical simulation that I mentioned in the beginning. Go back to there. So in these cases, we start from getting there. Or this one. So these one are actually coming from implicit surfaces. And so for this, or for medical images. So this one here, come on. Here, these one are coming from medical images, from CT scans.
Right.
For these sort of things, we now have a new system, which we are developing a plugin for 3D Slicer, where you can specify, you have an image, the image is already segmented, and then you can specify a map of which material are supposed to touch and which one are not supposed to touch. And then we have a way to generate meshes with this topology constraints enforced.
Okay.
So that's how we deal with this. I know that there are many models with overlap, but unfortunately, it's really like ambiguous, right? I mean, it might not even be, you can always construct a model where it's completely impossible to recover from an existing overlap. So my take on this is that I think this should be solved on the modeling side, getting rid of them instead of trying to deal with them later on.
Yeah, and then I have another comment just because, you know, there's a difference between collision detection and doing like, a consistent sort of approach for doing the transmission of stresses across the boundary. When you do these collision detections, you have a bunch of tetrahedrals. When you look at the stresses on them, they're not going to be smooth because of the way that the stress. So we bend over backwards to do these, approaches. They're like mortar approaches or these other kinds of approaches, which wouldn't be as nice to a large degree on some of these problems, I suspect. I guess the question is, you don't look at stresses very often in a lot of your calculations. And a lot of them you don't probably care, but there are some where we do. And I don't know if you've looked into some of that stuff. For instance, one of the things is that yes, you never penetrate, but sometimes you have to drive those curves together, like using an IP, interior point method. That we kind of need that. We can't get away with just keeping everything from penetrating. So it's a little bit more complicated from the engineering perspective of just saying we don't want anything to penetrate or we don't want anything to collide. We actually need to get hard stresses, or the right stresses at these interfaces. And it's just more of a comment than it is, because if it's an animation, I don't care, right? And that's part of the thing.
Thank you for the question. So this is a fantastic comment. And if you have data, I would love to try this because we do care about getting this to match reality. So in some of the papers, we actually have tests on this microstructure compressed.
And I think those don't have a problem. Yeah, those are good. It's mostly geometric in these cases, but there's simple cases where you just, you look at them and you go, geez, especially with TETs, you can get some really bad, stresses at where TETs basically are trying not to overlap, because you're not getting a consistent pressure across the two sides. So
so just fighting back a little bit on this. So with general contact models, I agree. Ours is actually C2. It's actually a smooth contact model. So you can think of it as having like around an object, your sort of pillow, which you can make as thin as you want, right? You can go down to like 10 to minus 6, 10 to minus 7. In there, the contact is smooth. So we are not discontinuous anymore. Like we are using the collision detection is done between triangles, of course.
Yeah, but say I put it in a position where each node is basically sitting on top of it's got a 0 penetration. Say I did IP method on this, and it's like almost 0. Everywhere you look on that surface, if you look at the stresses and the elements, it should be constant, but they're not. That's what I'm trying to say. It's a consistency condition that you lose out on when you don't do basically a variational consistent approach.
Yes.
That's all I'm trying to say, and it'd be interesting to talk more about that if you want some other time.
Yeah. Would love that. And
Mike,
just to see, like, of course, it's gonna go away under refinement, right? But you're probably not. You probably would like to have it on a discrete solution.
Well, it's not clear. It's not clear if it does. I mean, I can imagine it's not self-consistent, so to speak, or it is self-consistent. Actually, as you do refine it, it does the same thing. Anyways, it probably gets smaller if maybe you don't care on a lot of problems. But again, I'm a snob, so yeah, that's.
No, it's a great comment, and I would love to try this. We did not try this, so I don't know how quickly it becomes constant, but I would expect that it does become constant with this formulation under.
Well, I guess if you have to refine it to that degree, then maybe that's a problem too. So yeah.
Hey, can I?
yeah, maybe Mike, maybe you have some test problems that you can
Sure.
suggest.
I got a bunch. Yeah.
Hey, I have a ton of questions. I'm not going to ask them now, but they're similar to Puso's actually, to Mike's questions. So I don't know if there's a good time that maybe we could do another meeting. Maybe Mike Puso and I, and I'm sure Jerome and Brandon, a couple people will probably be interested in follow-ups. So I don't know, Zanya, you mind sending contact information?
Yeah, I can arrange a meeting. Absolutely.
And the other thing is the oil seems very nice, but it has a lot of numerical dissipation, and it is one of the reasons why we don't use it. If you're interested in things like dispersion and other things, if you're actually trying to model the waves, it doesn't do a good job. That's why people go to these second order methods, which, you know, is another thing to consider if you're looking at stresses and some of the mechanical responses. But obviously, you guys can, you know, deform these things to a much greater degree than we can on a lot of these problems because of some of these things that we don't want to give up on. So
just could you clarify what does it mean, like, to go to second order methods?
a second order time integration scheme. So Euler is first order in time.
Okay, this is third order BDF. All these simulations are third order BDF.
But I thought you were using when you show it, you usually show the first order.
That was just an example. Sorry, that was just to simplify the exposition, but this works for arbitrary order BDF.
Okay.
And works for arbitrary order elements. So usually we use like quadratic or cubic basis here. Otherwise, there is no hope of resolving stress at any reasonable level.
So also talking about the time integration that you're using, you know, you showed backward order, but you're saying you're also doing a higher order in time too.
Yes, higher order in time, yes.
Okay. Maybe somewhat related question real quick. What's the complexity of the algorithm with respect to the order of the elements? Some of the timings it looks like it's p cubed per element or something like that. Let me ask it a different way. Can you do 10th order element?
Oh, inversion, absolutely not. Well, I mean, like, but
it takes a while. It takes a while.
Yeah, it takes a while because the higher is the order, the more you need to subdivide. So you can see here how it grows. In 2D, maybe. In 3D, for a tetrahedron, maybe, but not with this precomputation. We require some smarter way to do it. For a cube, there is no hope.
Okay. This is a problem of interest for us. I know it's hard, but it's maybe something to look for in the future. And the other one I wanted to ask real quickly, you mentioned differentiability. That's really interesting also for us. This was all in PolyFEM, is that right?
Yeah, that's right.
And the differentiability, is this a Python code? Is that how it's done, or?
For now, it's C++, but as of last week, we have a Python interface for all the differentiable stuff.
So what's your method for differentiating the code?
Adjoint. It's an adjoint derived analytically on the continuous formulation, and we discretize after adjoint.
Okay, thank you.
And that was a lot of work, but Dennis Zorin is...
Yeah.
And so the paper for all of these, for the differentiable part, and also for the higher order time integration is... wait, sorry, I'm just... lost.
Get to see the talk again.
This one. So this paper here is the one that describes like how to handle these like contact, inversions, higher order time integration, and how to make it all differentiable.